Welcome to Train Signal. You're watching Configuring and Using VLANs and Private VLANs. So what are VLANs? Well, you probably know this if, again, you're getting ready to take the VCAP exam, but I think a little bit of review is in order, especially when we start getting into private VLANs. So virtual local area networks, or VLANs, allow you to have many virtual networks running over a single physical network. So it's basically logical separation of a physical network. It uses a standard format to tag Ethernet frames. It's called IEEE 802.1q. It's like a regular Ethernet frame, but with an extra 4-byte header. The information in the header tells the network device which VLAN the frame belongs in. While VLANs do logically separate traffic, if someone has access to the network segment, they can see all traffic. So if I can put a sniffer on a network port somewhere or a physical cable connection, anything that goes across that connection in front of me, I can pull off. Even if it's 20 different VLANs, I can see it. It's kind of up to the thing at the other end of the cable to honor that. Now, switches are different because if I plug my notebook into a switch port and that switch port is set to only let me access VLAN 5, I don't see other VLAN traffic on my cable. But if it's set to trunk and carry multiple VLANs, then I can see the traffic. So it's not always a reliable security method. It's really more about kind of this logical separation of multiple networks onto one physical infrastructure. And here's kind of a diagram. So it shows a simple physical network cable with two VLANs, VLAN 10 and VLAN 11, both running through the same single connection. Again, it doesn't increase bandwidth. You know, if that's a 1 gig connection, you get 1 gig total. You don't get 1 gig on VLAN 10 and 1 gig on a VLAN 11. You just get a gig. The number of VLANs you can use is often dictated by your networking equipment. VLAN number 0 is reserved, and VLAN 1 is the default most often, but I don't recommend that you use it. And the reason for that is fairly simple. In a lot of cases, all switches are required to carry VLAN 1 because it carries other communications, and you can't really what we call prune or stop VLAN 1 from being carried on all the switches. So if you have a lot of stuff on VLAN 1 and they're doing a lot of broadcasts, it's very hard to limit that. So anytime I do an assessment or a review and I see an environment where they put a lot of servers on VLAN 1, we have a little discussion about that and talk about why they really need to migrate that to a different VLAN and prune it back where it's not needed. Most equipment can go over 4,000 VLANs, but you may not be able to use them all at once. Very few people run into this problem. Normally it's a service provider with a bunch of customers, each with a couple of VLANs. But just to keep in mind, even though a switch says it can do up to 4,000 and say 96 or 94 VLANs, it may only be able to do like 1,000 of them at one time. Make sure you know which, if any, VLAN on the physical uplink switch is set as the native VLAN. So we talked about VLAN tagging a minute ago. So let's say I have a switch. I plug my vSphere host into it and I say, okay, switch port, I want you to carry VLANs 5, 10, 15, 20, 25, and 30. I want you to set VLAN 5 as native. What that means is when frames come out of that switch on VLAN 5, they have no VLAN tag. They just look like a normal frame. And my vSphere host has to be configured to say, look, if you see an untagged frame, assume it's VLAN 5. 10, 15, 20, 25, and 30 are going to have a tag on the front of them. I don't like setting things as native VLAN because I don't want to assume. And it's not so much the assumption, it's just I tag everything, therefore there is no exceptions and there's no questions. And if I come behind you or you come behind me, you don't have to guess whether that was a tagged VLAN or an untagged VLAN. So I recommend you tag everything. Now, I've mentioned this, I think, in the last lesson. I said, if we're good little admins, we would only trunk VLANs we actually need. But most people don't do this. I see it all the time where they've got their switch ports set that talk to vSphere set to trunk all VLANs. But really, if your servers are on VLAN 20 and your vMotion is 25 and your management is 30, those are the only ones you should be trunking. But because one day you may want to trunk 35, most people just do them all. That way you don't have to go back to the switch later. Doesn't mean that your VMs have access to all VLANs because you have to create a port group and you have to tell it what VLAN you're going to tag it on. But for the sake of good security and good control of network traffic, you really should prune those back and only configure your switches to pass the VLANs that are needed. As I mentioned, suggested not to use VLAN 1 unless you absolutely have to. Just a really good best practice. Now, there are 3 places where you can tag a frame with a VLAN ID. And this is where some people get confused. So, you can do it on the physical switch. This is what you do when you do not trunk VLANs to your vSphere host. So this sounds a little bit weird because you think, okay, if a frame's coming out of the switch, don't I want to tag it there? But it's really more about frames coming into the switch. So if I have a vSphere host, he sends a frame out and it hits the switch. If it's already got a tag on it, the switch won't tag it. It just leaves it alone. But if I tell the switch to tag it, it basically means that that is a native VLAN and the switch is doing the tagging. Then you have the virtual switch doing the tagging. So as a frame leaves the vSphere host in this virtual switch, it adds a tag to it. This is the most common method. Now, something to keep in mind, I don't think I mentioned a minute ago, is you can only have one VLAN set as native. Because you really couldn't see, if I got 5 frames without tags on them, I wouldn't know which VLAN they needed to go to. So you only set it to 1. So all 5 of those would be assumed to be the native VLAN of, say, VLAN 5. That's why I tell you to tag everything. And that's why I would say set your virtual switch to tag. That way everything is tagged, all port groups are configured for tagging and a specific VLAN number, and there's just less confusion. And then there's the guest OS. So basically what happens is that frames, as they leave the guest OS, are tagged with a VLAN ID. The vSwitch just passes them on down the line. The switch gets it. When the switch sends a frame, it's tagged. The vSphere host gets it, doesn't strip the tag off of it like it normally does, but it just hands it directly to the guest, and the guest has to have a driver in it for guest tagging. Very rare. I've seen this used for things like a firewall doing layer 3 routing who needs to understand VLANs. But it's rare. Normally what happens is we do the middle option, this one here. And when the switch sends a frame out, it's tagged. The vSphere host gets it. The distributed switch looks at it, says, oh, this is VLAN 5. He rips the tag off of it and hands it up to the appropriate VM because most guest OSs don't understand VLAN tags. So it's only tagged between the virtual switch and the physical switch. You can install an 802.1q driver in the guest. But again, it's rare and it's not something I recommend. Here's a quick diagram. You don't really, I would assume, not need to know anything like this for the exam, but just know that it's a 4-byte VLAN tag here, and it goes after the source and destination addresses so it doesn't mess with anything that might not understand it. So here's some diagrams for the different tagging types we talked about. So here's physical switch tagging. Port group is set to untagged. Frames crossing the connection have no VLAN tag. The switch port is normally set to what we call access mode, meaning it's an access port, not a trunk port, and therefore it is not tagging frames. You could also have a port group here set to untagged and set that as the VLAN that is native on that port. So you may tag some VLANs on some port groups, but the one you set as untagged needs to be set as native on the switch. Then you have virtual switch tagging. This is the one you probably want to use. So the port group is set to tag, and tags are applied as frames leave the switch and cross the connection, and the switch port is set to what we call trunk mode. Tags are inspected as the frames enter the switch and then switched out accordingly. Again, this is the one you see most often. This way, guests up here are not involved in the tagging and untagging process. They just see an Ethernet frame that's directed at them. And then we have the guest OS tagging, drivers in the guest. We set the port group to 495 or a range, depending on what you need to do. Normally it's 495. And you'll set the switch port to trunk because he doesn't know that which one of these things on the end is doing the tagging. He just knows that he gets a tagged frame. So again, rare, but a very specific setting. So, if you got asked on the exam to set one of these things up, just know you do have to set these to 4095. And again, here is a kind of a table format. So if the physical switch is doing the tagging, you would set the standard vSwitch for 0 or blank. And for VDS, you set it to what we say is none. For virtual switch, either the distributed or the regular who's doing the tagging, remember this is the most common, you specify the VLAN that it will be tagged with, and then the VDS is the same way. You set it for what it's tagged. You actually set it for VLAN and then the number. If the guest OS is doing it, you set a standard switch for 4095, or the VDS, you give it a range to trunk. If it's only one, you say, I want to do VLAN trunking, and I'm going to trunk this VLAN. Or you can say, I want to do VLAN trunking and this range of VLANs if you're going to send up multiple VLANs. That's if you did the entire range for the VDS, say 1 through 4094, 4095, I guess it'd be 4094, it would be the same as setting this. With the regular switch, you don't get to specify a range, it just does them all. With the VDS, you can specify that range. So while VLANs are pretty easy to configure, there's just little things to watch out for, some kind of gotchas. Again, I've said this like 18 times, but watch out for native VLANs. Setting a port group to the same VLAN as a native VLAN can cause communication problems. I've seen this a number of times. People will go in, create a port group, set it for VLAN 10, and that's what's set for native on the switch, and they don't understand why it's not working. If it's native on the switch, it needs to be untagged on the vSwitch. My suggestion is not to change the vSwitch, but to instead go and take it out of being native on the physical switch. Along the same lines, if you tell vSphere to tag frames from a port group, make sure the switch is set for trunking. That's what we just said. Trunk the VLANs you need and only the ones you need. Again, best practice. I wish more people would do that, but they don't. Recommend that you disable spanning tree on ports connected to vSphere hosts. There's an option on Cisco switches called port fast. So normally when you go up and you plug a vSphere host or something into a switch that's set for trunking, these switches do some spanning tree stuff. Spanning tree is a protocol. It's built to ensure that there's no loops in the network. Most people don't like spanning tree who deal with it because sometimes we wonder if it causes more problems than it solves. But anyway, the idea is sometimes spanning tree, depending on the implementation, will actually block traffic up to 50 seconds. What happens if I walk up, pull a cable out, and go, oop, wrong one, and plug it right back in? Well, the vSphere host sees a green link light and thinks that that NIC is up, but spanning tree is still doing its song and dance for up to 50 seconds. And so traffic doesn't actually pass, and you may notice timeouts. If you set to port fast, it speeds that up. It basically says, okay, I'm going to let you pass traffic, but I'm going to listen for things called like BPDUs and some other stuff, that spanning tree between switches. I'm going to listen for those, and if I see one, then I'm going to shut the port down. The vSwitch in VMware does not do spanning tree. It does other checks to confirm that there's no loops. So it's not going to send those special frames for the switch to detect. So it's not going to see it as an actual other switch that could cause a loop. So it's not going to see any spanning tree frames. So you should set it to port fast so it doesn't do its song and dance. Just keep in mind, if you do set it to port fast and accidentally plug in another switch and cause a loop, you can have a problem for a little bit until that's figured out. So be really careful. Just document this well, but it's suggested you do that. vSphere does not support negotiation of trunk settings. That is true. 5.1 distributed switch now supports a basic, what we call LACP functionality, link aggregation control protocol. It's not great, but it's a basic support, so it does negotiate some things. But for the current VCAP 5, keep in mind that there's no LACP support until they rev this exam for 5.1. Now let's talk about private VLANs. So the idea of private VLANs can seem very confusing, but it's really not. The basic idea is that you provide segmentation of devices that are on the same broadcast domain. So I've got VLAN 20, and I got a bunch of hosts in it. What if I don't want all those hosts to talk to each other? Normally I would do one of a couple things. I would do MAC filtering. So I'd go into the switch and say this MAC address can't talk to that MAC address, and this MAC address can talk to that MAC address. Well, that's a pain. You think IP access lists are bad, go do MAC address filtering. Okay, so we don't want to do that. So then we can say, okay, I'm going to put you on different VLANs and give you different IP subnet addresses, and then do access lists on a router or a firewall. Well, that's fine. But that can also chew up IPs, it chews up networks, and becomes administration overhead. So now we can do what are called private VLANs, which are kind of like VLANs within a VLAN. A common use and an easy way to explain this is with a DMZ network. So a DMZ network is a network you see in a lot of companies that exist outside the primary firewall, but often behind a secondary firewall. So it's hosts that are publicly exposed, but often not 100% exposed. And often it's different kinds of servers. It may be web servers, FTP servers, mail servers, things that may need to talk to each other like a cluster of mail servers, but not amongst different types. Like there's no reason for the mail servers to talk to the FTP servers. And the idea is we want to be able to control this without doing MAC address filtering or putting them all on different networks and doing IP filtering. And that's where we use private VLANs. Private VLANs use a concept of a primary VLAN and then a group of secondary VLANs. Continuing on, the primary VLAN is your main VLAN for the network segment. Think of it, if I say a VLAN within VLANs, the primary is that encompassing or encapsulating VLAN. The secondary VLANs provide the segmentation. And there are three types of secondary VLANs. There's a promiscuous VLAN, an isolated VLAN, and a community VLAN. Promiscuous VLAN, so devices on this VLAN can communicate with one isolated VLAN and multiple community VLANs. It's usually the same number as the primary VLAN. When you talk about VMware, it is the same as the primary VLAN. So if your primary VLAN is 50, your promiscuous VLAN is 50. You put things in this VLAN that are common. Firewalls, routers, stuff that everybody needs to talk to. So if I got a DMZ with a bunch of different type of hosts that I don't want to talk to each other, but they all need to talk to the router or the firewall on the edge, the firewall would go in this VLAN. Isolated. Devices in the isolated VLAN can only communicate with those on the promiscuous VLAN, the router, the firewall, but not other devices on the isolated VLAN. So let's say I had a group of independent servers. I had 3 FTP servers. They don't need to talk to anything because I'm afraid they'll get exploited and somebody will use them as a jump point. They don't even need to talk to each other. The only thing they need to do is talk to the firewall. I would put all those in an isolated VLAN. So even though they're all in the same isolated VLAN, the same secondary VLAN, and even though their IP addresses are on the same IP subnet, even in a row, one's .14, the next one's .15, the next one's .16, I can't ping them between each other. I can't talk. That's because the switch looks at it and says, you're not allowed to talk to each other. I'm going to drop this frame. It only allows you to talk to the firewall. And then you have community. So you can have multiple community VLANs. So you'll have one primary or promiscuous, one isolated, because there's no need to have multiple isolated VLANs, since isolated VLANs devices can't talk to anything but the one firewall or router. So there's no reason to have multiples of those, but I can have multiple communities. So let's say I have a group of mail servers, and I want them to talk, but not talk to anything else. I'd create a community VLAN, put those in that VLAN. They can talk to each other, as well as the router or firewall on the edge and the promiscuous. Then I had a group of web servers. They need to talk to each other for, some reason. I would put them in a different community VLAN. They could talk amongst themselves and talk to the promiscuous VLAN, the router, the firewall, but nothing else. Not the mail servers, not the FTP servers. So it's a way to segment those guys. So primary VLAN is your main for the network segment. Secondary VLANs provide the segmentation inside. And here's a little chart. So promiscuous can communicate with one isolated, multiple communities used for common devices. Isolated, they only can communicate with things on the promiscuous VLAN. Nothing else, not even other things in the isolated. Used for servers that only need to communicate to the common devices but not each other. And then community devices, they can communicate with devices on the promiscuous VLAN and other devices in the same community VLAN. So that's for like a group of servers or a farm of servers that need to communicate with both each other and things in the promiscuous network such as a firewall. So here's an overview of how you would configure this. You set your primary VLAN as say 100. Your secondary VLAN will also be 100 for the promiscuous network. This is how we'll set it up in the distributed switch. Then you'll have a primary VLAN of 100 with a secondary of 101 for isolated and a secondary of 102 for community. I could have another community here of 103, 104, 105 down the list, and this gives you an idea of what they can talk to. So here's a little diagram showing my secondary VLANs within the primary VLAN. And here's a diagram example. Blue is things on promiscuous, inside and outside firewalls. Orange and yellow are two communities. So orange is a DNS cluster, they pass zone information, and an application cluster where they talk to each other, say a front-end web server and a back-end database or something like that. And then red is isolated, email and FTP that have no reason to talk to each other, nor any reason to talk to the other things. So this is your classic DMZ example and use case for private VLANs, and I think it kind of spells out the purpose of this. So configuring this is fairly simple. Now, private VLANs are only supported with the VDS or the Nexus 1000V from Cisco, and it's a two-step process. We don't talk about the Nexus, not covered under VCAP, but I just want you to show that that's the only two ways to do it. This regular vSwitch can't do it. Configuration is a two-step process. So in the main VDS config, you associate primary and secondary VLANs, and then when you create a port group, you specify in the VLAN assignment, hey, this is a private VLAN, and it's either the primary, the community, or an isolated. So it's a two-step. The overall config is done in the main switch, and then on a port group by port group basis, you specify if it's promiscuous, isolated, or community. So in the lab, we're going to do this. Review the configuration of private VLANs with the distributed switch, configure promiscuous, isolated, and community VLANs, connect some test VMs, and then show the actual segmentation. One other gotcha that I need to mention before we jump to the lab, before I forget. With VMware Switch, your physical switches have to support private VLANs. Cisco Nexus 1000V does it itself, so you can actually use this without switches that understand private VLANs. But when you do it with VMware, you have to have switches that support it. So just keep that in mind as well. So with that, let's go ahead and let's jump in the lab. So here we are back in the lab. So what I've done is I've kind of set us up to test out and kind of demo private VLANs. So I've created 5 Windows XP systems. One is going to act like a router or common device. I've put kind of their purpose out to the side to make it easy. So this will be in the promiscuous mode of the primary VLAN. Then XP2 and 3 will act like servers that shouldn't talk to anything, even each other, except for the common device. So those will be in an isolated VLAN. And then I have 4 and 5, which will act kind of like a server farm or cluster, so they can talk to each other and only the other common device, so they'll be in a community VLAN. Now, if you want to do this at your own lab, you can do like I've done it. My physical switches don't support private VLANs, so I have got all these guys sitting on the same host using a DRS affinity rule. If we go look, settings, DRS rules, I have an XP group runs on a VM, so we can expand this and have all my XP systems. So I have 5 of those VMs in this VM group called XP systems, and I just created a cluster host group which is Optimus in it, and I told it that they have to run on that. So now we're ready to go and create our private VLAN. So remember, the overall config is done on the main switch. So we'll do edit settings, private VLAN, and start our configuration. So I'm just going to kind of make up some VLANs that I know aren't being used elsewhere. So we'll do 150. And then you create your primary and then your secondaries underneath it over here. If you add another primary, say 250, these will be considered separate. So you could have a primary of 250 and then isolated in communities, and then a primary of 150 with some other isolated in communities. So you only put your primary on the left. So I'll delete this. There we go. And then we start adding our secondary VLANs. So I'll make this real simple. 151. Tab this down, and we'll make this the isolated. Remember, you only have one isolated, since there's really no reason to have more than one. And then 152 is community, and you can have multiple communities because you may have multiple server farms You want to talk amongst each other, but not other things in other community VLANs. But for this purpose, we'll just do one of each. And we'll say OK. So once that's complete, we have to create our port groups. So the first one I'll create is our promiscuous group. You set it to private VLAN, and then you get a second box here where you pick your primary or your secondary VLAN. So this one I'll do primary. Good. Do the next one. Isolated. Private VLAN. Isolated. And then the last one. So port group. Community. Private VLAN again, and then the community. So done and done. So now we have these. So we'll go back to our VMs, and we'll go one by one and put them in the right port group. Edit settings. Now I've already assigned these guys static IP addressing and all that stuff separate from the rest of my network. So if you do it in your own lab, keep that in mind. They won't have access to the main DHCP server or anything like that. So promiscuous on the Nash Lab distributed switch. And I'll just walk through these real quick. Isolated. Isolated. And then my two communities. Community. And community. Okay. So now that's all done. Let's do a couple of things. So first of all, we've got promiscuous, and we'll see here. So let's go ahead and console. And let's bring up a DOS prompt. CD. All right. So what I've done is I've given these latency again. Is I've given these guys the IP address on 10.0.0.0 really. So this is .1. So let's see. XP2 is 2, XP3 is 3, 4 is 4, 5 is 5. So I should not be able to ping anything. Oh, I should be able to ping everything. Forgot I was on the common device. So he should be able to ping everything. And that does seem to be the case. So this were the firewall. He could talk to all the systems. So now let's go look at one of the isolateds. Go to console. All right, so here's earlier testing when I set this up. So again, he is .2. He should be able to ping, and we saw this a minute ago, he can ping the common if I learned. Actually, that did work, but just to show that. He should not be able to ping anything else since he's in the isolated. So he shouldn't be able to ping his partner, which he cannot. And he should not be able to ping anything in community, which he cannot. So the two isolated systems can only talk to the common device. Even though they're on the same IP subnet and everything, they can't do it. So now let me show you one of the communities. Console again. There we go. He's .4, so again he can ping the common device. Yay. He should be able to ping his buddy .5. Yay, yes he can. But he can't ping either of the isolateds. And he cannot. So there you go. So what we've done is we've shown the difference between community VLANs, isolated VLANs, and the primary or promiscuous VLAN. So that shows you how you can basically do layer 2 segmentation without having to do MAC filtering or anything like that. And that's the function of private VLANs. So that's it for this. Let's jump back to the slide deck. So now let's quickly hit the vSwitch security configuration. There are 3 standard security options, and these show up on standard vSwitches as well as distributed switches. Promiscuous mode, MAC address changes, and forged transmits. Remember that incorrectly setting some of these can cause problems, especially when it comes to clustering and load balancing, because they may need to do things like MAC address changes or forged transmits as they handle load balancing. And basically, they may have a virtual MAC that floats back and forth between a set of, high availability boxes or virtual appliances. Promiscuous mode basically says if you allow this, you can set a VM's virtual NIC to be able to intercept any traffic going across on the same VLAN in that port group. So it basically is used for kind of a packet sniffer, not nearly as powerful as port spanning within the distributed switch. MAC address changes and forged transmits are a little bit confusing. It's basically whether you're talking about inbound or outbound, really. So MAC address changes says if a VM tries to change its MAC address and you set this to reject, it will not allow frames to come in from the network through the switch and be delivered to the VM. So if you change it, frames won't be delivered to the VM from the switch. Forged transmits is the opposite. If you set this to reject and a VM changes its MAC address and tries to send a frame, it'll be rejected by the switch. So really, if you want to change MAC addresses, you need to set both of those to be allowed, or to accept is actually the command. They can be useful for stopping impersonation attacks, things like changing MAC addresses to help bypass security controls. By default, I would suggest setting these all to reject, again, unless you have a specific reason. And if you do, I would create a different port group, even on the same VLAN, and only attach the VMs to it that need these options to be allowed. So I wouldn't do it on like the server port group. I would create a port group just for that. And here's a quick little screenshot. We'll see it again in the lab in just a minute. And real quick, every VM who has a NIC, which is pretty much all of them in pretty much every case, has a MAC address, one MAC address per NIC. And just in case you need to know this, where they come from. So they are stored in the VM's VMX file. You'll see that they're Ethernet 0 generated address, meaning the vSphere host generated that for it. And it's generated when a VM is first powered on, and then it is kept. It's stored in the file, and it's kept with the VM in case you need to have kind of a, the set MAC address. You don't want to go changing that every time you power on the VM. So once it's created, powered on, that's generated and put in the config file. It's created using like the first 3 bytes of it are VMware's what you call OUI, Organizationally Unique Identifier. So everybody that makes NIC cards, Intel, Broadcom, QLogic, Emulex, and people who make up virtual NICs, VMware, Microsoft with Hyper-V, Zen Server, stuff like that, all have a unique OUI. That way the idea is that you don't get 2 NICs with the same MAC address. At least that's the idea. And so since VMware's not shipping NICs, they have to come up with some way to try to uniquely do this. So the first 3 bytes are their OUI. If the VM is started from the vSphere host, it uses vSphere's OUI 00C029. If it's started from vCenter and not directly from the host, it uses vCenter's OUI 005056. So probably most of the ones you see in any managed environment is going to start with 005056. The last 3 bytes are based on a couple of things. First is the SMBIOS Universally Unique Identifier, the UUID for the physical ESX host. That UUID is burned into the ROM, or the BIOS really, of a server. It should be a unique identifier. Again, each server manufacturer should have their own unique prefix for that. I have actually seen them where they're all zeros from some clone systems, which is kind of odd. It has caused issues in other areas, but it should be unique. And then it's a hash based on the name of the virtual machine. So the idea here is the VMware OUI is always the same, kind of like 3COMs or Broadcoms would be. But then they try to randomize the rest of it using a unique identifier from the server and the name of the virtual machine, which may or may not be unique across your environment or multiple environments. So now let's jump in the lab. This will be real quick. We're going to look at the configuration options for vSwitch security and just show you where you see the MAC information for a VM in case you've never seen it. So back we are. Let me jump up and just at least get out of this. So let's go to networking. And we'll do it on a port group. We'll do that one. Manage the port group. And security under policies. And here you go. So you can see by default it's reject, reject, reject. And you could go and change these to accept. And this again is done on a port group by port group basis, not at the main switch level. If we go to a host, up at the top, configuration, networking. Let's go to a standard switch and do properties of a standard switch. What you're going to see is these are actually set at the switch level. So if I edit the switch, they're done at the switch level on a standard switch, and it defaults to reject, accept, accept. So you may want to go and override those. So that has changed between the two. And again, one is set on the switch and the other one there. You can actually override, so you can override this. So the VM network port group. Let's see, yep. So you can basically say, do you want to override this? And by default, it does override the switch parameters. So just a little difference there. So here it's all accept, which is kind of not what I would want to do, but that's where it's set in the lab right now. So again, you can set it on the switch and then override it in the port group. But those three options have not changed in a long time. So again, anybody, I kind of default to what I say is VCP level knowledge, but most people have seen those. And if you ever dealt with Microsoft load balancing or anything like that, you may have even had to change those. So in case you've never seen, the MAC address, we'll pick a host, or I'm sorry, a VM. I'll use my domain controller. I'll edit the settings. I'll go to the network adapter, and right there is your MAC address. Notice it's automatic and not manual. If I click one that's not powered on and check it, you can actually override this. But again, it's not going to let you override this with something odd. So let me do that again. Manual. Let's see if it'll let me change this 57. 121212. Yeah, see, it won't do it. Is invalid. Actually, I think that's too many numbers. Nope. It wants you to keep using the VMware OUI. That way you're not going to accidentally have a conflict. So that's where you do the MAC address, and that's where you can do a manual override if you have to do so. So again, said it was going to be a short lab. It was a short lab. Let's jump back to the slides. And that's it for the lesson. So a couple of things that I would focus on for the exam, especially the functionality of private VLANs, what the different uses are for the primary, for the isolated, for the community. Understand that it's a requirement to use VDS for that. Understand that you configure those VLANs first in the overall switch config in the private VLAN tab. Then you have to create the port groups for each one and attach the VMs. I'd also keep in mind that you need to have physical switches that support private VLANs, and those have to be configured with the same matching primary, isolated, and community VLANs as well. And then just know where to look for MAC address information, how to change it and override it if needed, and just understand that piece, and as well as vSwitch security, just in case you get a question around, hey, you're doing a load balancer and they need this, or you want to do a packet sniffer and they need that. Understand where you set those at. So that's it for this lesson. I look forward to seeing you on the next one.